Thank you very much. Thank you very much, Elizabeth, for the invitation. I want to thank you and all the organizer of this program, and also, of course, the Hausdorff Research Institute for Mathematics for hosting this nice program. The main motivation to study valuations on function spaces comes from the theory of valuations on convex bodies. So the start of my talk will be on exactly on this topic, and I will start with a very quick overview on this subject. So what is a valuation? So let me fix some notation. I will work, at least in the beginning, with the Kn, which is the family of convex bodies in Rn, which are compact and convex subsets of the Euclidean n-dimensional space Rn. And valuation is a functional defined on Kn. For me, it will be always a real-valued functional, with the property that if you take two convex bodies K and L, such that the union is still a convex body, then you have this additivity law. So zeta of the intersection plus zeta of the union is just the sum, zeta of K plus zeta of L. So this is basically an additivity property, a finite additivity property of your functional, which you have to check only when the two convex bodies are such that the union is still a convex body. So in a situation like the one that you see in this picture. There are surprisingly many examples of valuations, and probably you all imagine that the most common example you can think of is the volume. So the volume is a valuation because it's finitely additive, and it's much more. But then you have other examples, and I want to mention, for instance, intrinsic volumes. So for instance, the boundary measure of a convex body is a valuation. This is quite surprising. And then you have other functionals, like functionals that you can obtain by mixed volumes. We will see later how to construct these functionals. In the previous talk of this series, they were in some sense at the center of the talk. So mixed volumes, and there are still more examples. Another example I wanted to mention is a fine surface area, which is also an example of valuation. This is particular because differently from the other, it's not continuous with respect to the natural metric on Kn, so it's a sort of different example. Now, you understand it would be impossible for me even to give a very rough overview of all the results that have been proved in the theory of valuations in convex geometry. Because this is a very big portion of classic and modern convex geometry. So recently, or quite recently, a few years ago, we saw the second edition of the monograph by Rolf Schneider, where there is a whole chapter devoted to this subject, which is a good survey on the subject. You can find many of the relevant results there. Of course, I have tried to list the people who contributed to this theory, and this is the result. And for sure, this list is not complete, and I apologize with all those who should be mentioned and are not. Nevertheless, I would like to mention three results on valuations on convex bodies for two reasons. The first is that they are cornerstones of the theory, and the second is that I will return on them by a different point of view, by an analytic point of view. Maybe most of you can imagine which results I'm speaking about. Anyway, the first is the Hardware Theorem, which is a very simple, deep, and elegant result, and says that if you have a valuation defined on convex bodies, real valued, which is continuous and rigid motion invariant, then this valuation will be a linear combination of intrinsic volumes. Continuity will be always intended with respect to the Hausdorff metric in Kn. This result is very rich. First of all, it's a complete description of rigid motion invariant valuations on Kn. It tells us that the space of this valuation has a finite dimension. It tells us that intrinsic volumes are a basis of this space, and also it gives us a homogeneous decomposition for these valuations, because each intrinsic volumes is homogeneous of a certain degree, depending on the index I. And then every rigid motion invariant valuation can be written as a sum of homogeneous valuations. This phenomenon, that evaluation can be decomposed as the sum of homogeneous valuations, as a finite sum, goes beyond the assumptions of this theorem. Is valid under weaker assumption concerning this rigid motion invariance. And this leads us to the second result, which I want to mention, which is the homogeneous decomposition theorem by Peter Mcmahon, which says that if you have now a valuation which is continuous and translation invariant, so now the difference that you have to notice with respect to the previous result is that we pass from rigid motion invariance to translation invariance. Then you can decompose your valuation as the sum of n+1 valuations, Zi, and Zi is a continuous and translation invariant valuation, which is I homogeneous. And the meaning of homogeneitis is very straightforward. I mean, everybody can imagine what is it? It's just by ordinary dilations of convex bodies. The landscape of translation invariant and continuous valuations is big, and a very important class of valuations with these properties are those which can be obtained by mixed volumes. So we arrive to the third result, which has this preamble. So assume that, consider the mixed volume functional. So V is the application from Kn to Dn into R plus, which associates to n convex bodies their mixed volumes. Then you can do the following thing, very simple. You fix an index J and you fix some convex bodies. So K, J plus 1 up to Kn are fixed. And then you consider the application which assigns to K, to a convex body K, the mixed volumes, the mixed volume where the first J slots are occupied by K and the remaining ones are occupied by the bodies that you have fixed in advance. And this is a continuous and translation invariant valuation on Kn, which is J homogeneous. And then there is a theorem which solves a conjecture by Peter Mcmahon. And this theorem was proved by Semyon Alesker. And this theorem says that valuations of this form are dense in some appropriate sense in the class of translation and translation invariant and continuous valuations on Kn. Okay, this is more or less the end of the first part of the talk, in which I wanted to speak a little bit about valuations on convex bodies and mention these three results. And then now we turn page and we switch to a different type of valuations, which mean valuations defined on spaces of functions. We will return on these results at the end of the talk. So, of course, I will start from the definition. Assume that you have a space of functions, which for the moment I will call X, but it will be some specific examples later on. Assume that you have a functional defined on this space, which I call with the same letter as in the geometric setting. And you say that this functional is a valuation if the following happens. However, you take two functions in your space, U and V, the value of your functional at the maximum plus the value of your functional at the minimum of these two functions is equal to the sum of zeta of U and zeta of V. Of course, you have to take care of the fact that the maximum and the minimum of U and V are still in the space you started from. Here, with this symbol, I denote the pointwise maximum and the pointwise minimum of the two functions. I'm sorry, here there is a misprint. This should be U, as you can imagine. So this is the definition. I hope that the definition explains itself in a clear way. The passage from sets to functions is just done by replacing union and intersection by the max and min operation. As we will see, this choice is quite natural. What I want to say now is that there are a lot of examples of functionals with this property, and I want to start with a specific example, which is in the next slide, which is this. So the function space is the space of continuous function on the unit sphere of Rn. So C of Sn minus 1. And then you define the functional in a very easy way. You just take the integral of your function over the sphere with respect to the n-1 dimensional Hausdorff measure on the unit sphere. And it's really very easy. It's an easy exercise to show that this is a valuation. You just do it by hands. And then you see that there is nothing special with the integral of u. You can take the integral of u square. You can take the integral of e to the u. And you can take a lot of things. And in general, if you fix a function k, which is continuous from R to R, and you take the integral of k of u over the unit sphere, then you have a valuation on C of Sn minus 1. There is a notational problem in my talk, but this is not something that I discover now. I use the same letter K to denote a convex body and this function here. But I choose I choose K again here just as a kernel. I want to see it as a kernel function. And I hope that there will be no ambiguity in the talk. This type of valuation have several interesting properties. Let me stress that, for instance, they are continuous. So this functional integral of k of u of x is continuous with respect to the natural topology on continuous functions, which is the topology connected to uniform convergence. And also, it's rotation invariant. I mean, if you apply your functional to the composition of u with a rotation, you get the same value. And as we will see, I mean, I didn't mention as a coincidence these two properties, and we will see it later on. But these examples was intended as a sort of opening for the general setting of valuations on spaces of functions. So in all the examples that we will encounter, we will see spaces of functions defined either on Rn or on the unit sphere. And the reason why, and the reason is that I want to consider valuations with geometric invariance properties. So I need to have translations and rotation at disposal. So I don't want to fix specific domains. I will consider valuation which are continuous with respect to the natural or anyway some topology on the space of function that I'm considering. And I will very frequently consider valuations with some geometric invariance, rotation invariance or translation invariance, or also vertical invariance, which means that the valuation doesn't see the addition of a constant to a function. So zeta of u is equal to zeta of u plus c for every constant c. Sometimes I will consider the valuation with this property. And another kind of invariance is that with respect to the addition of linear functions. So sometimes I will require that zeta of u is equal to zeta of u plus L for every u in the space and for every L linear, whenever this will be possible, of course. So as it is mentioned in the title of this talk, this theory, the theory of valuations over spaces of functions, is quite recent. And for this reason, I mean, all the results, or I hope all the results which have been proved in this theory can be listed just in one slide. So there was results on the space of definable functions. I'm not an expert in this area, so I will not go into any detail concerning these spaces. There have been works on classical function spaces like LP spaces, Sobolev spaces, BV functions, and so on. Continuous functions on the sphere, as I said, Lipschitz functions on the sphere, and then there is a group of spaces of functions which are connected with convexity, and this is quite natural, starting from the assumption that everything originates from the theory of valuation on convex bodies. And so the spaces of functions are the space of convex functions, quasi-concave functions, log-concave functions, and so on. So the reason, by a personal point of view, why I approached this subject of valuations over spaces of functions, the reasons are basically two. The first was this question: is it possible to have some analytic proofs of results regarding valuations on Kn? And the second, which is similar but different, can we have analytic counterpart of these results? So can we build a functional version of the theory of valuations on Kn, including possibly results like Hadwiger, Mcmahon, or Alesker's theorem? In the rest of the talk, I will try to say something about both questions, and you will see that the answers will be quite different from each other. But let's start from maybe the historical beginning, or at least one possible historical beginning of the story, which is the work by Dan Klein on valuation on star-shaped sets. So Klein started to study valuations not on convex bodies, but on star-shaped sets as the counterpart of valuations on convex bodies. And he considered a specific class of star-shaped sets, namely that formed by those sets with a radial function belonging to some LP spaces, or more precisely to Ln. So he was assuming that the radial function was belonging to Ln of the unit sphere. Remember that the radial function of star-shaped sets measures the distance of the boundary point from the origin, the boundary point that you encounter if you are moving along a ray of some direction belonging to the unit sphere. He could prove a characterization result for valuations defined on this class, and the result is very neat, is very simple and complete, I would say, and is the following theorem. If you have a valuation tilde zeta on the space Sn, and you know that this valuation is continuous and rotation invariant, then this is possible if and only if it can be represented in the following way. So the valuation over some set S is the integral over the unit sphere of K of the radial function of S, where K is a kernel function and is a function from R to R, which is continuous, and it verifies some growth assumption at infinity, and this is necessary in order to guarantee that this integral is finite. Remember that rho of S is in Ln. And the continuity of the valuation is intended with respect to the distance induced by the Ln norm of radial functions. Now here we can see a passage from sets to function. Why? It's very easy to see that you have two star-shaped sets, S1 and S2. The radial function of the union is the maximum of the radial functions, and the radial function of the intersection is the minimum. This is geometrically immediate. Then if you have a valuation on star-shaped sets, you can transfer this valuation on the sets of radial functions. You define zeta of rho as zeta tilde of S, where rho is the radial function of S. So the result of Klein can be rephrased as a result on a family of functions, and in particular on the space of Ln plus. Plus means that you take functions from the Lebesgue space Ln, which are non-negative. So you have the following theorem. If you have a valuation on Ln plus of the unit sphere into R, which is continuous and rotation invariant, then this can happen if and only if it has the form that we saw before. So it's the integral of some continuous function of rho over the unit sphere, and this function K has to be continuous and verify some growth assumption condition at infinity. This theorem was extended from the specific Lebesgue space Ln to a general Lebesgue space by Zhang in 2010. I think that the result of Zhang was part of his PhD thesis, I guess. And I wanted to mention the title of the paper by Andy Zhang, which is Valuations on LP Spaces. So the passage has been done here. The paper by Zhang is intended as a paper on valuation on spaces of functions and not on sets anymore. And you see that the statement is very similar of that of the theorem of Klein, with the difference that now the class is LP and P can be whatever between 1 and infinity. 1 is included, plus infinity is not included. But the structure of the theorem is the same. I'm sorry, I'm making some confusion. So Zhang proved two theorems. One was exactly similar to that of Klein on the unit sphere, but he also proved the corresponding theorem on the whole space. So for functions belonging to LP of Rn. So here I only wrote the theorem on LP of Rn. You may notice that in this second theorem, you don't need rotation invariance. You only need translation invariance of your valuation. While on the sphere, the corresponding assumption was rotation invariance. Let's come to a further development of this line of research, which is the set of continuous functions on the sphere. This is another theorem that I like a lot because it's a deep result with a very simple and elegant statement. It was proved by Villanueva and Tradasete in two papers, in which they mention the work of Klein, but they also, underline the analytic flavor of their result. So they prove the following. Assume that you have a evaluation on the space of continuous function on the sphere, which is continuous with respect to the uniform convergence, so the L infinity norm, and which is rotation invariant. Then there exists some kernel function k from R to R such that zeta of u is equal to the integral over the unit sphere of k of u of x in dx. By the way, this covers also the L infinity case, which was not included in the paper in the previous paper by Andy Zhang. I think that this result, in some sense, is a suggestion, is an invitation to go further, to analyze other spaces, and to discover new valuations, in a sense. And so my idea was to go in the direction of regularity, of more regularity. So, for instance, C1 of the unit sphere or C2 of the unit sphere. So which are the valuations which are in some sense available on these spaces? Of course, imposing continuity conditions and also probably invariance conditions. I have to say that the research in this direction did not have important developments. Probably, I don't know whether maybe this is not the right point of view, this is not the right question, but there were not so many progress in this direction. Of course, we are expecting more valuations, because in general, if you narrow the space of functions, you have more valuations, because the additivity condition, you have to check it on less functions. And probably in the valuations that you will have, you will see derivatives, because usually valuations tend to use all the available properties of functions of a given space. Let me mention that another space which is, for me, is very interesting to study is the space of support functions. So this is a subset of continuous function over the unit sphere. For every convex body, you can define its support function h of k, which is defined on the unit sphere. For instance, you can extend it to the whole space, but you can even see it just on the unit sphere. This measures the distance of supporting hyperplanes from some fixed point, from the origin. And you can see support functions as restrictions to the unit sphere of one homogeneous convex functions in the whole space. So assume that you have a valuation on convex bodies. You can immediately transfer your valuation on convex bodies to a valuation on support functions in a very easy way. You define zeta tilde of h of k as zeta of k, and zeta tilde will be a valuation. This is quite easy to see. So you have a correspondence between valuations on convex bodies and valuation on the space of support functions. So you may hope to prove the results on valuation on convex bodies in some analytic way. Note that rotation invariance goes into rotation invariance, continuity goes into continuity, and translation invariance in the geometric setting goes into invariance under the addition of linear functions. So everything is ready. And one could hope to prove, for instance, the Hardware Theorem in some analytic way, Mcmahon Decomposition Theorem in an analytic way, and so on. And this was one of my initial ideas. But I have to say that this project failed, more or less, because I think that I didn't even get near to prove something like this. It's a sort of dead end. Anyway, still, we continued the investigation, which started with continuous functions, at least in one direction, and together with Daniele Pagnini, Pedro Stradaseta, and Ignacio Villanueva, we considered valuations on the space of Lipschitz functions on the unit sphere as a continuation of the study of valuations on continuous functions. Why Lipschitz and not C1? The reason is very easy. Lipschitz is closed under maximum and minimum, while C1 is not. So it's easier by the point of view of valuations. Our general conjecture was that there could be a classification of continuous and rotation invariant valuations on the space of Lipschitz functions on the unit sphere. And we were expecting something like this, some integral involving the function u and its gradient, its spherical gradient. This was a conjecture. We didn't prove this conjecture. We made some steps in the direction of this conjecture, but roughly speaking, we are quite far from a complete proof. We got a result in one special case, imposing not just rotation invariance, but invariance with respect to the addition of linear functions. So let me state the theorem that we have. So assume that you have a valuation defined on the space of Lipschitz functions of the unit sphere, and assume that it is continuous. I didn't tell you about the topology that we decided to take. It's a reasonable topology. It doesn't really matter for this exposition, so I didn't want to go into the details. Anyway, there is a topology with respect to which zeta is assumed to be continuous and rotation invariant. And then we assume that our valuation is invariant under the addition of linear functions, so scalar products, restrictions of scalar products to the unit sphere. And then we discover the following fact, which is a little bit strange. You can decompose your valuation into 3 pieces, and these pieces are very well defined. Everything is very rigid in this case. So the first is a constant. The second is just the integral of the function, not a function of u, but the integral of u. And the second, it's even stranger. It's the integral over the unit sphere of this expression. So u squared times n minus 1 minus the norm of the gradient square. I'm wondering now if any of you is trying to guess where does it come from. It comes from a specific thing, which I hope it will be clear in a few minutes, but you may try to guess. So you have in some sense, you have a homogeneous decomposition of your valuation, because zeta 0 is 0 homogeneous, zeta 1 is 1 homogeneous, zeta 2 is 2 homogeneous. But then you are in dimension n, and the decomposition breaks at the second order. Why? Well, I will say something about the proof of this result, and I hope that it will be clear why. So, about the proof. The fact that valuations of this form have all the desired properties, it's easy. And of course, the hard part is the reverse. So I'm assuming that I have a valuation with all the properties specified in the previous slide. What do? I take the set of support functions which are continuous, and they are also Lipschitz because they are restrictions of one homogeneous convex function. So they are Lipschitz on the sphere. So I have this subset, and I have my valuation. My valuation has a lot of invariance properties, and I know the behavior of my valuation on support functions because basically, by a geometric point of view, I know that it's translation invariant and rotation invariant and continuous. So I can apply Hardware Theorem. And I have a decomposition of my valuation, zeta, not on Lip, but on a subset, which is the subset of support functions. Basically, these zeta I are intrinsic volumes, okay? So I'm using Hardware, and Hardware tells me that zeta 0 is just a constant, zeta 1 is the mean width, and zeta 2 is V2, and now you see where does this expression come from. You can write the second intrinsic volume of a convex body in this way using its support functions. Maybe this is not a very common way to see convex body V2, but it's possible. And you see that this expression only involves the support function and its gradient. Then you made the following discovery: the remaining valuations, zeta 3 up to zeta n, they cannot be extended to the whole space. This is the point. So we proved the following lemma: if you have a valuation on the space of Lipschitz functions, which is continuous, rotation invariant, and invariant under the addition of linear functions, such that it coincides with an intrinsic volume over support functions, and the intrinsic volume has an index bigger than 3, bigger than or equal to 3, then your valuation is trivially 0. The proof of this lemma was the heart, I mean the crucial part of the paper, and basically the reason is that you cannot express intrinsic volumes starting from V3 without the use of second derivatives of support functions. And for this reason, you will never be able to extend them to Lipschitz functions. Once you have this lemma, the rest is quite easy. So you have your valuation zeta, you know the behavior over support functions, and you know that there is a fracture, and before the fracture, everything before you can extend to the whole space, everything after you cannot, and then you prove that you are left with the first part of the decomposition. We tried to go in the direction of the conjecture I was telling before, but we made some progress, but the picture is far from being complete. So have been considering general valuation defined on the space of Lipschitz functions without invariance under the addition of linear functions, only with rotation invariance and continuity, but we only obtain some partial results in this case. I have some minutes left, and I would like to conclude the talk speaking about convex functions. So since several years in collaboration with Monica Ludwig and Fabian Musnig, we are studying valuations defined on convex functions. To be more precise, in our last papers, we have been considering a very specific class of convex functions, which are supercoercive functions, which I will explain in the next slide. And it turned out that in this class, we see something. And in fact, we have a counterpart of the homogeneous decomposition theorem of Mcmahon, and we have a counterpart of the Hardware theorem for rigid motion invariant valuations. You remember I mentioned 3 results on valuations on convex bodies, and the third result is also true in this area, and this is a very recent result by Jonas Knör, who was able to establish a density result in the same spirit as that of Alesker for valuation on supercoercive functions. I have to say that the work of Knör is not in the setting of supercoercive function. He is working in a dual setting, but his results can be transferred to the setting of supercoercive function. So let me try to explain, at least in part, these results. What are supercoercive functions? These are functions which are defined on the whole space. They are convex. They might attain the value plus infinity. They may not attain the value minus infinity. They are Lowell semi-continuous, and they go to infinity faster than linearly. Okay? So the growth at infinity is prescribed. It must be superlinear, a superlinear growth at infinity. We can keep this space with a rather natural notion of convergence, which is epiconvergence, which coincides with uniform convergence on compact sets when you are dealing with finite convex functions. Why this space? Well, at the end, why this space? Because it's the only space in which we were able to find Mcmahon and Hardware. But the fact is that these results are not true if you drop the supercoercivity assumption. So it's really, in some sense, it's really necessary to make this assumption. We are considering valuation defined on this space, which are rotation invariant and sometimes and/or epitranslation invariant. What does it mean, epitranslation invariant? It means that they are invariant with respect to vertical movement and with respect to translations. So you can translate the space variable, you can add a constant, but you don't change the value of your valuation. By a geometric point of view, epitranslation invariance has a very simple meaning. It means that if you have 2 functions such that their epigraphs differ only by a translation, then the valuation has the same value at the 2 functions. Okay, so this is the meaning. This is also in some sense necessary for what I'm going to say, in the sense that if you drop vertical invariance, for instance, the next result fails to be true. And the next result is a homogeneous decomposition theorem, which tells you that if you have a valuation on this space, which is continuous and epitranslation invariant, then it decomposes into the sum of homogeneous terms. So here you see the sum, and each term of the sum is homogeneous of order I. So I'm sorry, here there is another misprint. This should be zeta I, of course. The rescaling that you do of your function u is not just the multiplication, but is this rescaling, which in the dual setting is the usual multiplication. And here is a rescaling which rescales epigraphs. So the epigraph of lambda u is lambda times the epigraph of u. So it's epi-homogeneity in some sense. It's interesting to mention that there are many valuations with these properties, like in the geometric setting, and a big class of, I'm sorry, some remarks before, which I forgot to say. In the proof, we use Mcmahon decomposition theorem. If we drop supercoercivity, we lose the validity of the theorem in the sense that you don't have homogeneous decomposition. And as I was saying, there is a dual result for finite convex functions, which may be obtained just by usual duality in convexity. So Legendre conjugate. So what I was saying before is that there is a class which was introduced by Semyon Alesker recently of continuous, homogeneous, and epitranslation invariant valuation on the space of supercoercive functions. And here you see the action of Alesker's valuation when your function is C2. And here the conjugates appear. This is a strange expression. The expression becomes easier in the dual setting, and it was introduced by Alesker in the dual setting, but since we are working in the supercoercive setting, I wanted to state it this way. So here you see some given function m, and then a mixed discriminants with given matrix value, with given matrix valued function pairing, which are fixed, and then you have your function u here. And you have to think about this Alesker's valuation as mixed volumes. And in fact, Knör was able to prove that they have this role because these mixed Hessian valuation are dense in the space of continuous and epitranslation invariant valuation on this space. Let me just close on Hadwiger. For Hadwiger, we need intrinsic volumes. So we found at the end of a very long story intrinsic volumes. At least I hope that we found intrinsic volumes, and they are of the following form. So you have your function u, and you define a valuation in the following way. You integrate over the whole space a kernel function zeta depending on the norm of the gradient times the elementary symmetric function of the Hessian of your function of order n minus k, which means that you take all the eigenvalues of the Hessian matrix and you take the elementary symmetric function of the eigenvalues, which is the sum of all possible products of distinct n minus k eigenvalues. Of course, you can do it only if the function is C2, but in the next slide, we will see that you can extend this, type of valuation. My time is over. I will just steal 2 minutes. What was really hard for us was to understand the condition on this function zeta such that this integral is well defined. This was really a long story. At the beginning, we thought that it was just continuity. Continuity is enough, but it's not the end of the story. You may have discontinuous zeta for which the integral is well defined, and in particular, zeta may have a singularity at the origin, and the integral is still well defined, and has all the nice properties that it should have. And at the end, we understood that there is a class of zetas, which we call Hadwiger class, and you see the definition here. So the definition depends on the index k, and you have these two conditions. So the zeta may be singular at the origin, but this limit has to be 0, and this integral here has to be convergent to a real number. Then we prove that our intrinsic volume is extendable to the whole space of supercoercive functions. So this object here admits an extension to the whole space which is continuous. And these are the things that you have to put in the Hadwiger theorem. So if you have a valuation on your space which is continuous and epitranslation and rotation invariant, then it must be the sum of the intrinsic volumes that I showed you before. And this is the end of the talk.